Our senior project is to improve on the design of a device that allows a user to tow a riderless bicycle behind their own in a safe and effective manner. This project originally came to us from a recently retired Cal Poly professor and local businessman. He wanted to answer the question of, how do I transport two bicycles at once without the use of a car? So he often wanted to pick someone up from downtown SLO and needed to take them on a bicycle to ride back home. All of the group members in this project ride our bicycles on a daily basis, so we definitely saw the need that this specialized device could provide. We thought that the bike-friendly town of SLO would be a great place to design and introduce a product like this. So our project will cover the design and manufacturing aspects of achieving this goal and considering the economic justification of producing and selling this product.
Our client needs a biking tow system that is easily adjustable, detachable, and commercially viable. He wants it to be manufacturable at his factory.
When our client gave us this project to work on, he also gave us a functioning prototype to use as a baseline for applying our design improvements. This prototype attached to the chainstay of the bicycle as shown here, and it also attaches to the rear luggage rack. It uses hose clamps to attach to the chainstay and an unconventional fastener of a gear tie to attach to the luggage rack. This prototype had some strengths. It was functional. A bicycle could be towed behind it. It could be attached to several different size diamond frame bicycles, and it was easy to operate, meaning that when you were riding it, it was hard to tell that you were actually towing a bicycle behind you. However, this device also had some problems. The attachment at the chainstay is a potentially weak point on the bicycle. Tools were required to screw in the hose clamps, and fasteners were non-standard and fostered inconsistent fastening. There were also operational errors, meaning that when you took a left turn, the tire of the bike that you were towing skidded on the ground. And when backing up in reverse, the bike tended to fall over. Also, a luggage rack is required to attach this device to the bicycle.
Our research fell into four main categories: patents of existing designs, bicycle frame strength, failure and reliability testing, and manufacturing methods like welding.
We made a house of quality and a failure modes and effects analysis chart to gain an understanding of the limitations of the initial design and provide focus for improvement. Throughout the design process, we made SolidWorks models of our designs and used the built-in simulator to do deflection and stress tests. This helped us pinpoint areas for improvement for subsequent prototypes.
Due to the limitations of our mechanical expertise and our focus on industrial and manufacturing engineering concepts, dynamic or vibration testing was not pursued. If this project is to be further developed into the future, these additional design considerations must be considered.
After analyzing the problems with the initial design, we built our first prototype out of 3/8" steel to reduce the weight. We fastened it to the seat post and the chainstay to eliminate the need for a rear luggage rack, and we raised the towed bike's front wheel higher off the ground to eliminate the problem of the tire scraping on the ground on left turns. Unfortunately, this design revealed huge stability issues, and we realized that the further a bike was off the ground, the greater the chance the handlebars would rotate down and the bike would collapse. Our next prototype lowered the bike closer to the ground, but still attached to the seat post and the chainstay. The design had good vertical support, but poor lateral support, and the addition of the towed bike caused it to lean into the rear tire of the lead bike, preventing movement.
To overcome this significant problem, we utilized a rear luggage rack during our testing, which successfully prevented contact with the tire. As a result of this design change, Prototype 2 had no advantages to our current state model, and was actually slightly deficient in terms of stability and ease of operation.
Realizing stability was the major failing point of the previous prototypes. Our third design fits over the rear wheel and attaches to the eyelets on either side of the rear hub and the seat post, creating a rigid structure. We switched back to 1/2" steel for rigidity. The hook bar that held the tow bike is suspended under the structure, close to the ground. The stability and smooth operation in the final design is noticeably better than the initial design. The tire scraping from the initial design has been eliminated. The final design can be assembled without tools, and there is no need for a luggage rack. However, both designs can still cause the tow bike to fall over when backing up.
Our field testing for each prototype consisted of two different categories, attachability and functionality. For attachability, we recorded several different times for both attaching the device to the lead bicycle and securing the towed bicycle to the device. Our functionality testing was more qualitative. With the help of a GoPro, we were able to observe the device in action at a close range and at higher speeds. The testing involved a variation of speeds and maneuvers, which gave us a solid understanding of the performance of each device.
The device is manufactured from a single piece of solid, round steel bar stock. It is first cut into the appropriate lengths, and the sharp edges are grinded down. The members that form the main structure are bent 110 degrees, and the ends are pressed flat and drilled. Then the hook bar is bent from a single piece. Finally, the assembly is welded together.
In addition to functionality improvements, our final design had significant improvements related to the manufacturability of the product. We prototyped our final design to eliminate as many welding joints as possible. For example, creating the slot for the towed bicycle front wheel involved only 2 bending operations with a cold bending machine. The original state model involved 2 bending operations and 2 welding joints to join the C-hooks onto the slot. Eliminating welding joints will not only improve the appearance of the device, but it will eliminate possible strength quality issues. Additionally, the final prototype utilized cold bending in place of welding joints to make the rigid frame structure. Overall, this reduces the number of operations, cycle time, and reduces quality variation. Our main focus for the economic aspect of this project was to consider how much it would cost and what kind of facility is needed to manufacture a quality product of this kind. From our research, we determined that an initial investment of approximately $5,500 is required for this production. If we want a 100% rate of return and a machine depreciation life of 5 years, we wanted to figure out what is the required annual volume and how is this volume affected by batch size. We have several key assumptions for this economic analysis. Firstly, this is built-to-stock manufacturing. Second, all units that are produced will be sold, and the selling price of those units are $60 a piece. Only 1 employee will be working in this facility. We want a 100% rate of return. We are analyzing this investment over 5 years. We have a 40% tax rate. Storage costs are $1.50 per square foot. To outsource the powder coating operation would be $25 per unit. An inventory turn is 10 times per year. And a labor cost is approximately $18 per hour. Using the equation for calculating cash flow, we determined the annual volume required for batch sizes of 5, 10, 25, 50, 75, and 100 units to break even in our investment. We then graphed these values, and based on the graph, we determined that a batch size of 50 is the most efficient way to manage labor and storage costs for this production. Here's a breakdown on the left of the unit cost and an analysis of the cash flow on the right.
Ultimately, a device like this has the potential to expand the capabilities and decrease the limitations that adopting a bicycle-powered lifestyle could offer. This lifestyle is beneficial to the environment, healthy for the individual, and financially practical.